Okay. Well, today we get to do the fun stuff. All right. Now, yesterday, Jason talked extensively about the standard model Higgs, specifically how you look for it, but he also, in setting that up, told you how you produce it in the standard model and how it decays in the standard model. And so to finish up with what I was going to say the last time, didn't quite get to, let me re-emphasize a couple of points that he made. One of them is that if the Higgs is light, it decays predominantly to bottom quarks, just because there's not anything else for it to decay to which it couples strongly. And in fact, it doesn't couple very strongly to bottom quarks. So it is rather narrow, and the coupling is rather weak. Whereas when it becomes heavier than twice the W mass, or even quite a bit before that, it begins to decay to W's and Z's. And even when it gets heavier than twice the top mass, it doesn't decay that often to tops, because it decays predominantly to Goldstone modes. And what controls the coupling of the Higgs to Goldstone modes? That is to say, to the W longitudinal W's. What coupling controls that? Turn off the gauge couplings. What would be important for the Higgs? There's this coupling. There's this coupling. And for the Higgs, that would be everything. This is a potential which has a minimum, has Goldstone modes. And what controls the coupling to the Goldstone modes is this. And remember, the mass of the Higgs in the standard model goes like lambda. H squared goes like lambda v squared. There's some 2, which I don't care about. So if I make the Higgs heavier and heavier, I'm making lambda bigger and bigger. I'm increasing its coupling to the longitudinal modes of the W and Z as I go. So it doesn't couple that much to the top by the time it gets heavy enough to decay to the top. So predominantly it decays to W's and Z's, and it gets wider and wider and wider as a resonance the larger lambda becomes. We'll come back to that. Okay, but I want to first talk about the light Higgs. Before I do that, actually, just coming over to the board, I reminded myself of what I wanted to say. Just as an aside, so many of you, I think, are aware that in TASI 01, I wrote an introduction to SUSY. What you may not be aware, but it's quite relevant given where Seiberg sort of ended and what he wasn't able to cover, is that in my TASI 03 lectures on the duality cascade, the whole first chapter or two is an introduction to Seiberg duality. So you may find that useful as a supplement or an explanation of many of the details of what Seiberg did not get to explain in his last lecture. I don't talk so much about the superpotentials that he covered, but I talk more about the dualities between gauge groups and cover it with some care. Okay, so what I want to do first is talk about what would happen if Jason and his friends are dealing with a world where the Higgs sector is not minimal. For example, as Michael mentioned just this morning, there could be supersymmetry, in which case we have 2 Higgs doublets, which means we have 5 Higgs particles, or it could be the next to minimal supersymmetric standard model, where we have an extra complex field S, which then gives us 2 additional real Higgs fields to play with. So there's going to be lots of Higgs particles that they can decay in all sorts of funny ways. What sorts of things can happen? Well, basically, everything. The production rates can change. Of course, there are multiple states that you could be dealing with, so they all have different production rates. The decay rates can change. The coupling to photons that is used to find lighter Higgs in some cases can go down or it can go up. The production rates can go up, but usually they go down for each particle, which is never good. And it's a very, very complicated story. But let me give you a sense for how complex it can be by just considering not a supersymmetric minimal, non-minimal extension, but first the sort of leading next to minimal standard model itself. So I'm going to do something which leaves all of the successes of the standard model, doesn't screw up flavor, doesn't screw up all the electroweak precision one-loop tests of the standard model. I'm just going to take one additional real scalar field and add it to the Higgs potential. Okay, so here are all the terms that you would write down. The usual Higgs potential, quartic and quadratic terms for S, and then a quartic coupling between the two. S is for singlet. But it's not the S that we had in the previous lecture, which was complex. This is real. It's not supersymmetric. Okay, don't worry about the fact that, this is not a particularly well-motivated model per se. What I want to illustrate is the phenomenological issues So I'm not suggesting you should take this model seriously. The real situation is worse. Okay? So now what happens in this model? Well, we know that for this model to make sense, H must get a VEV, which is V over root 2. Since S is a singlet, it wouldn't break electroweak symmetry. So we still need that Higgs VEV, just as before. So you can substitute H is V over 2 plus little h, V plus H over root 2 into this potential, and I leave it as a little exercise. What are you going to get? Well, you can sort of see what you're going to get. In particular, you're going to have, of course, a mass term for the Higgs, and you're going to have a mass term for S, which will be some combination of these parameters here. And very importantly, this term, the S squared H squared term, is now going to give you a term which is eta, its coupling, times the VEV of the Higgs, times H S squared. Which means that if S is lighter than half the Higgs mass, you now have a new decay mode. So now our Higgs can decay to SS. Well, if S doesn't have an expectation value, you notice that this potential has a Z2 symmetry. So S is the lightest particle carrying that Z2 symmetry, therefore it's stable. Right, the Z2 symmetry just S goes to minus S. So since there's a Z2 symmetry, S goes to minus S, and S is stable, and S just doesn't carry any standard model quantum numbers, it's invisible. So we've just opened up a decay mode where the Higgs decays invisibly. And the coupling, well, it depends on eta. It could be big. It could be small. Now, if the Higgs is light, this decay mode is competing with this decay mode. And the coupling here is y sub b, which is not very big. So without working too hard, I can make this bigger than that. And now most of the time, the Higgs is decaying invisibly. All the other decay modes go down. The branching fractions stay proportional to each other, just as before. But they all go down by a certain factor. And the branching fraction, invisible branching fraction, becomes very large, maybe essentially 1. It is possible to find an invisible Higgs, probably, although it's very hard at the LHC. But this is one lesson which you should keep in mind. One new particle can ruin your whole day. Okay? It's a very important lesson. We spend a lot of time talking about minimal models and learning how the minimal models work. For a theorist, adding this extra scalar, why would you do that? I mean, the model's basically the same. It's still the standard model. You've just added one. It doesn't change any of the basic properties of the standard model. But for an experimentalist, you have totally changed the world. So for theorists to only think about minimal models from the point of view of actually finding this stuff is very dangerous. We have to keep this in mind. And that will be a theme which will come back again throughout the lecture. OK, any questions?
So if you toss this into somebody's global fix to the standard model, precision electroweak or something like that, is it truly invisible?
It will have essentially no effect, because S, the only thing you've added are things that couple through H. That's right. And now you're talking about at the best two-loop effects, and it only involves this thing. I haven't gone through the numbers, but because YB is small, this doesn't have to be that big to be a big effect. OK, now there are other things you can do with this model. Suppose you change the parameters so that S has a VEV. Now that means we've broken the Z2, and that might have cosmological problems, but let's ignore that. Now, if S has a VEV, then this term, the S squared H squared term, has terms that go like, there are terms that go like HS, as well as H squared and S squared. Right? There's a term which goes like eta times V, and let's call the VEV of the S field, did I call it something? Let's just call it S. Okay, so now that I have HS terms, and of course I have H squared terms and I have S squared terms, and that means these things mix. So I have to diagonalize the mass matrix. So now, instead of having H and S, they mix. So I have two new eigenstates, phi 1 and phi 2, which are mixtures of H and S. And now S can decay, because S contains a little bit of H, and H can decay. So both phi 1 and phi 2 can decay now. That's good. And I can produce both phi 1 and phi 2 directly via glue Higgs, for example. Glue goes to Higgs, for example, because each of phi 1 and phi 2 has a little bit of H. So I can produce both of these things with cosine squared of some angle, with the sine squared theta of some angle. which is the mixing angle between the two. So I can produce them, and they can decay, but interesting things can happen. For example, maybe phi 1 is larger than 2mw, and phi 2 is smaller than 2mw. So this one decays to w's, and this one decays to b's. Right, so I can find a Higgs, and it decays to b's. And I say, I found the Higgs. But I'm not done yet. There's going to be another scalar here that decays to w's. Actually, of course, we'd find them in the opposite order. Just because we find a Higgs that decays to w's doesn't mean there isn't one that decays to b's. And if m phi, which one was the heavier one? If m phi 2 is greater than or equal to twice twice m phi 1, well then, for the same diagram that I had over there, we can have decays where phi 2 decays to phi 1, which then decays to BB bar, or BB bar tau tau. So now I've got even a larger set of decays that I have to consider. Yeah?
Can I ask a question about your original scenario?
Yeah.
So it seems like what you're saying is that the signature of this model would be that you would just never see the Higgs?
You would never see it directly. You would only see it through missing energy, which you have to infer it. Yeah.
Yeah, but
I mean, be careful with never. This would still be there, but at a very small rate.
yeah, but I think so. You argued in the first lecture that if the Higgs is not there, you have a catastrophe.
No, I didn't say the Higgs is not there. I said you can't see it.
Yeah, but I think you would still infer that it's there because you would see that
Yeah.
you being perturbative. So you would say, aha, there's some Higgs and there's some.
No, you wouldn't. You would say something is solving this problem, the unitarity problem, but I don't know what it is.
Yeah.
It wouldn't say that there's a Higgs or that it's perturbative. You wouldn't know what was going on. So you really do want to find this and actually say the problem is there is a Higgs there, it's fairly light, but it's decaying invisibly. That's quite distinctive from saying, well, there's some other more subtle things that are prevent. For example, here, let me just point out, this case is I can't find the Higgs because it's decaying invisibly. This case is I can't find the Higgs because phi 1 is not produced very often, and phi 2 decays mostly to phi 1s, and I have 4b's, and it's hard to see a resonance in 4b's. Totally different conclusions, okay, but I can concoct many more. So there is a risk of hiding the Higgs through various mechanisms and making it more difficult to find. And one has to keep that in mind. Okay. Yeah?
When you say this in the first scenario here that it decays invisibly, I suppose I'm not following. Why isn't the detector picking up S?
S doesn't carry any standard model quantum numbers, so it interacts even more weakly than neutrinos. No charge, no color. Okay, now, it might not be so bad. For example, what's the question?
There must be some virtual effect. I mean, given that the
Well, you already heard about the virtual effect yesterday. The virtual effect is we think the Higgs is light because we think the standard model is, if the standard model is correct, we can see that the Higgs mass should be between, let's say, 75 and 300 GeV. That's not very satisfying. If I don't see something explicitly, is it because the standard model is correct and this thing is decaying invisibly or this way? Or is it because the standard model is wrong and there's some conspiracy such that, I mean, virtual things are not the same as, holding something in your detector. Okay? You can't be sure if you have just a bunch of virtual, because circumstantial evidence is not the same as direct evidence. Now, it is possible, for example, that there is a small S cubed term. Since this violates a global symmetry, or I should say a discrete symmetry, which might indeed be gauged, so it's actually consistent with string theory, a small violation of that could be, is not unnatural, right? If you throw in a small coupling, you should explain why it's small. Well, a small coupling can remain small under quantum corrections if, when it goes to 0, there's an additional symmetry. So a small explicit breaking could be there. And if that's the case, we could go back, well, we could go through these scenarios, but in any case, we could go back to this case, and then S would not be exactly stable. And it also could mix just a little bit with H, even without having a VEV. So what we would have is that S, in this case, lives a long time and then decays to BB bar. So what would we see in our detector in that case? Potentially, well, if it lives too long, we see nothing. It's invisible. If it lives a very short time, we see something just like this, 4 Bs. But there's a sweet spot in between where what we see is, drawing the detector now with, and here's the looking at the detector with the beam in the center here, and here's the tracker, and here's the little beam pipe. So what we see is, somewhere in the middle of the detector, suddenly, there's all these tracks coming out of nowhere. And out here, there's a blob of energy with nothing pointing at it. Now, if you listen carefully to Jason's talk, you know that what happens when they run the tracking algorithm on this thing is they don't find the tracks, at least not the first time around. Because the tracking algorithms don't look for things that don't come from right here, or very close, because there's so much other junk running around. So this is great. There's no standard model background to this process. But that doesn't mean the detectors will pick it up if you're not careful. So it's very important to think about things like this, which could be discovered if you ask the right questions experimentally, but which, for example, might not be triggered on, or if you don't ask the right question, or even if they're triggered on, may just go into a big pile of weird-looking events that no one ever sort of takes seriously enough to say, wow, that's the Higgs. Now, in fact, this particular type of thing is possible in various models. It was not searched for until, well, the first publication was last year, and it wasn't. The search began 2 years earlier. It was hard. And they only are able to look at the tevotron for various technical reasons for events where you have 2 decays inside about 20 centimeters, which still leaves a lot of room for possibilities, and even their limits there are not so strong. So the Higgs could have a very high branching fraction in this scenario and be accessible at Fermilab and yet not have been identified, even though they have a couple of thousand Higgs bosons produced if it's that light. So this is not easy to do, but it's doable. Yeah?
If you also consider the electron-wave precision measurement constraints on your parameter.
No effect. S can only show up at 2 loops. Think about it. S only couples to H. Take any precision electroweak calculation you want. It starts with standard model particles other than the Higgs on the outside. The Higgs would appear at 1 loop. The S would appear at 2 loops. And I never said here these couplings had to be that large because they're competing with a very small coupling. So there's just no constraint. Can have a... It still doesn't constrain it. Because S doesn't couple to anything except H. So it doesn't affect any standard model particles that we know about yet. It just affects the acceptor. Go home and think about it. I mean, I think this is a good model to practice with. All right? So the lesson is, I do want to move on because I have other things to say. But the lesson here is, again, you change the model by a very small amount from a theorist's perspective. You can change the experiment in dramatic and very different ways, depending exactly what phase of the theory you're in. And you can make things which you thought were very hard very easy, at least if you ask the right question, or extremely difficult. And there's no way to know which it's going to be. So we have to approach the LHC and the LHC era with very open minds. Even if we're totally convinced as individuals it might be supersymmetry, or that it's going to be the standard model, maybe with a slightly complicated Higgs sector, that still leaves, experimentally, a huge range of things that could happen, and difficulties, therefore, in interpreting what we actually find. It's going to be a long haul, and there's a lot of smart people involved in it. Now, just to emphasize another point here, this model isn't elegant. Okay? It doesn't pass Occam's razor, right? If I hand you this model and I hand you the standard model, you say Occam's razor would tell you take the standard model. Why do you need this extra thing? Okay, but I want to introduce another concept. Okay, this is Strassler's machete. Okay. Strassler's machete is a different way of cutting theories apart, and it has to do with the issue of the importance of model building, which has multiple roles. One important thing about model building is figure out what the world actually is. You know that most of the models you write down in your life are wrong. In fact, for most of us in this room, every model we write down in our lives is wrong. So why are you doing it? Well, you're guessing, of course. There's sort of 2 things you might be trying to do. You might be trying to elucidate some particular idea of how some deep problem in particle physics might be solved. And even if you get the wrong model, it doesn't matter because you may have gotten the right concept. But there's another purpose for model building, which is to exhibit important types of physical signatures to look for experimentally, which if no one's thought about, no one's looking. So Strassler's machete is a criterion such that a theory is important if it predicts a non-obvious signature, such as that one, which nobody has, or very few people have thought about enough, so it hasn't really been considered by the experimentalists yet, could be observed, and would not be observed, or is unlikely to be observed, by accident, using the methods that are already available. Now, if you invent a model that they're going to find anyway, okay, that's nice, but the model's probably wrong, and unless it had a deep idea in it, it's fine, but it doesn't change what the experimentalists do, it doesn't really change theory, it's just a decent model. But a model can be important if it changes what we do in experiment, if it suggests a new experiment or a new use of data in experiment. And I encourage you to take such models seriously, even if they don't look pretty for a theorist. If they make a difference for experiment, they're important. Okay. I will now get off off the podium and go back to some other beyond the standard model physics. Any questions or comments?
Sorry, as you covered, like in your second scenario,
Yeah.
you have phi 1, phi 2 mix. It's a mixture of Higgs and S.
Yes.
So phi 1, phi 2 can couple to standard model.
Yes.
So that
How much do we know about the Higgs mass right now? It's between 75 GeV and 300 GeV. You should get a sense for how little we know. Okay? We really don't know from precision electroweak very much about the Higgs sector. And the 2 Higgs doublet model that shows up in supersymmetry isn't very constrained either. And there you have 5 Higgses. Why aren't you worried about the fact that supersymmetry has 5 Higgses? Shouldn't we be able to constrain it already? No. Go through the numbers. I mean, these are quantitative questions. We're nowhere close to being able to constrain the Higgs sector. There's little places where we can, but not very much. And certainly not with singlets. With more doublets, there are constraints. But with singlets, it's really not much, because they don't couple to the electroweak gauge bosons. Okay. Yep.
can you comment on the loops effect of S in loops?
Go home and try it. Exercise. Figure it out. Okay. Put in some numbers. Determine for yourself whether you should worry about this stuff. These are all the same question, and the answer is no. Let me turn now to models beyond the standard model. This was sort of a homily to general issues. I want to get to actual models that solve or attempt to solve the hierarchy problem. And to do that, I want to remind you what the hierarchy problem is. Now, you've heard it from me once. You've heard it from Michael a second time. But I'm going to give you a third perspective on the same problem. Because when you build models to solve the hierarchy problem, there's an essential, fundamental tension that you have to deal with. And all models come up against this. So in the standard model, there are 2 things which involve the Higgs. One is that sort of involve the properties of the Higgs in a sort of direct way. The kinetic terms for the Higgs are always the same. They're universal because they just involve couplings to the gauge boson. But the real problem is the mass term for the Higgs boson, which, of course, we have to understand why it's small, but also the Ikawa couplings for the fermions. I've written them just sort of generically as some doublet fermion and a singlet fermion coupling to the Higgs. The details won't matter. The problem is, if we muck with this, we're potentially mucking with that. And it may not be easy to deal with both of them. And in fact, this is the essential problem. These 2 terms want 2 very different things. This term would prefer that the Higgs was not a fundamental particle. Because if the Higgs is a fundamental particle, this is dimension 2. That means mu squared is dimension 2, and it should be of order some high scale, like the Planck scale or the string scale. And then we have to play all sorts of games. So one way to deal with that is say, well, the Higgs is not a fundamental particle. It's a composite. And therefore, the mass will be at the same scale as the compositeness. Okay, that's perfectly reasonable. That's what happens in QCD. QCD hadrons have masses of order the compositeness scale, with the exception of the pines, which can be a little lighter. But things like the rho meson and the sigma, their masses are all around the confinement scale. But if I do that, how do I get this? Now I have to couple all the standard model fermions to whatever is making the Higgs composite. And that's tricky if we're going to get that whole pattern. Basically, what we're forced to do is have the theory of how the Higgs was composite be tied up with the theory of how the standard model fermions got all their Yukawa couplings, and thus their masses. So it becomes very complicated to imagine how you build such a model, even in principle. And then when you practically do it, you run into flavor changing neutral currents very easily, because you're adding all sorts of new effects that involve flavor. And it's hard to get another thing in the standard model right, which is that most of the Yukawa couplings are pretty small, but the top quark Yukawa coupling is big. Actually, it would be pretty easy to do a compositeness model if all the Yukawa couplings were small, because then you would say, well, the Higgs is composite. That pushes mu squared down. And because it's composite here, this is secretly some high dimension operator. And these dimensionful couplings are secretly a ratio of the compositeness scale over whatever is the mass scale that suppresses this high dimension operator. But the top quark Yukawa coupling is 1. Not square root of 4 pi, which would be big, but 1. Big enough that it's not so easy to do that. So then you start thinking, well, maybe the top quark itself is composite, and it participates in the compositeness. Maybe everything else isn't. And then you realize, well, okay, for the top quark's composite, there's a left-handed top quark, there's a right-handed top quark. The left-handed top quark is in a doublet with the B, so the B quark is composite. But we've been looking for interesting flavor physics in the B system for about a decade, and we don't see any. So that doesn't sound so good. So we're sort of pushed into a corner where it's just the right-handed top quark that's composite if we're going to make this work, and yet but the left-handed top quark does come in here. I mean, how is this all going to work? So the essential tension between these two things is really important to understand, because anytime you try to make the Higgs composite or it's somehow strongly interacting, to affect this term, to solve the problem of the hierarchy by pushing this down, you're going to push these things down and have trouble with the top quark. And then, in solving that problem, that's going to determine how the model works out. Okay. Now, there are, of course, various approaches to this. One is supersymmetry. Supersymmetry solves this problem by playing particles and the sparticles, the particles and the sparticles, off against each other in the way that has been described to you a few times. So I won't say more about that for now. The point, of course, is that that cancellation is imperfect because supersymmetry is broken, and the cancellation, in order to get the Higgs mass to be of order a few hundred GeV scale, has to involve SUSY breaking at the TeV scale, and not much more. Okay, so we know SUSY broken at TeV. In our sector, it might be broken at much higher scale in some other sector, and then mediated to us by gauge dynamics or gravity dynamics to give us this scale. Now, if you talk about strong dynamics in composite, so some sort of composite Higgs, then there are all sorts of varieties. And I will not say too much about them today, simply for lack of time. But Technicolor is one class, and I will describe these later. Another example is often called the little Higgs. These are both ways of keeping the Higgs mass under control through some sort of compositeness, and having strong dynamics, in this case, at around the 1 TeV scale, and in this case, around the 10 TeV scale. Now, since this is strong dynamics, if you squint a little bit, you say, well, there should be some versions of this idea which have ADS-CFT duals, so there should be some extra-dimensional versions of these things. So there's some warped extra-dimensional models, which are basically versions of this. They differ a little bit because, well, I mean, these models might be smaller tough coupling models like QCD, and these might be larger tough coupling models, and maybe they're not very precisely defined. In fact, you could be sure they're not very precisely defined because most of these are non-supersymmetric. So people are sort of guessing that, well, okay, maybe there are non-supersymmetric ADS duals that have this behavior, and they calculate what happens. And they're reasonable. They're self-consistent. You can worry about whether they really exist as theories. In some cases, they don't, but some of them do. Now, there's one other possibility, which is large extra dimensions, and that's really a totally different idea. That's the idea that really the solution to the hierarchy problem is really the Planck scale is at the TeV scale. And we're going to run into quantum gravity head-on. Not some quantum gravity that's really dual to gauge dynamics, but just plain quantum gravity. And you might say this is an example of a larger idea, and maybe this is too radical. But maybe what you want is the idea that what we're up against is that the hierarchy problem is resisting solution because quantum field theory, which is at the heart of our whole discussion about what the hierarchy problem is about to break down. Which is a little hard to believe that we haven't seen any sign of it yet, and it's going to break down at the 1 or 2 TeV scale, but it's not obviously impossible. So we should at least keep that in mind. So maybe this is too radical, but something radical might still be in the cards. And then, of course, there's the possibility it's just the standard model, and plus denial. There is no hierarchy problem. Okay? It's just a selection effect. We're in the landscape, and we live here because if we lived somewhere else, we'd be dead. It's been argued that argument is hard to really justify in the situation of the weak interactions, but maybe it's true. It still raises the question of how it's possible that it's true, because it doesn't seem obvious that you couldn't move the weak interactions around and still have a world in which you could have structure and observers and so forth. But we do have to deal with this possibility. That might not be so good experimentally, but we have a lot of work to do on the theory side. All right, so let me talk about supersymmetry now. If there are any questions about this, I should stop first. Yeah.
So you say that supersymmetry solves this problem, but that mass term is actually supersymmetry.
Yeah, I don't want to discuss that because Michael will discuss it, I assume. You're going to say a little more about the mu problem? Yeah. Let me just leave it a question. Okay, so now what I won't do, there's a page in your notes, the last page of the last lecture, which describes supersymmetry and all its properties, and Michael's basically touched on them, so I won't go through it again. But what I do want to emphasize, or re-emphasize, is that supersymmetry, if you just take it off the shelf, implies, if you write down all possible operators that are allowed by the symmetries, large baryon number violation. Protons decay, and this lecture is over. Okay. We have to deal with this problem. Now, what people say is, and this is important, we add something separate. This is not part of supersymmetry. We add a discrete symmetry. It is usually called R parity. And because it has an R in it, people think it's part of supersymmetry. But it's important to notice that if I combine it with fermion number, I could instead write it as just a matter parity, just a discrete symmetry which commutes with supersymmetry. And in a lot of ways, it's good to think about it that way. All the superpartners basically are odd under this thing. And all the particles we know about are even, if you think about it as R parity. But it doesn't matter. Point is, R parity solves this problem. It eliminates the dangerous terms. But because it's a new global symmetry, it does something else. It means that, just as I had earlier for the Z2 that reflected S, it implies that the lightest R odd particle is stable. And all of the superparticles of the Standard Model are odd. So there's a possibility the lightest one is stable, though we have to be a little careful about that. So there is, if we take the point of view that all superparticles, for all sectors, in all the full Lagrangian of the universe, including all the particles, if the lightest supersymmetric particle is this particle, and typically it is, so let's assume it, the LSP, the lightest supersymmetric particle, the lightest superpartner of anybody, is stable. That, I emphasize, is a consequence not of supersymmetry, but of R parity. If I broke supersymmetry but preserved R parity, this would still be true. So when people say supersymmetry predicts a dark matter candidate, because it predicts a neutral stable particle, be careful. R parity predicts the dark matter particle, not supersymmetry. Now, why does it do that? All I've told you is that the LSP is stable. Well, if I have some new stable particle that's relatively light, can it be electrically charged? We would have found it by now. So the answer is no. Can it be colored? If you have stable charged particles, they're produced in the early universe, stable colored particles, they're produced in the early universe. They float around. A few of them land in the Earth. They fall to the bottom of the ocean. We scoop up some ocean water or mud at the bottom of the ocean, and we look through a mass spectrometer to see if we find any atoms that are heavier than they should be. Because these things will bind to atomic nuclei if they're colored, and they'll bind to electrons if they're charged. There should be atoms out there to find, and we don't see them at a very, very, very high level. So it's pretty clear these things are excluded. They also cause problems for nucleosynthesis, yada, yada, yada. If you have a new stable particle which is light, it's neutral and colorless. Neutral and colorless. And therefore, it's a dark matter candidate, potentially, if you make enough of them. But in any case, it's something which could be the dark matter. So it's R parity combined with our knowledge that such a particle can't be charged or colored, which gives us the dark matter candidate. Okay? Now, the big difference, and this is not a sharp difference, but the big difference from the point of view of what we heard earlier today between gravity mediation and gauge mediation is the mass of the gravitino, which is set by how big F over M Planck is. M3 halves, in the gravity mediation case, typically is of order TeV. And there are standard model superpartners, which are typically lighter than that. So let me define something, which is not usual notation, but it's still important to have some notation for it. The LSMSP is the lightest standard model superpartner. Okay? It's take all the standard model particles, including the Higgs, and take all the superpartners. The lightest one of those is this particle. Now, in gravity mediation, the gravitino is heavy, so the LSMSP is the LSP. Well, assuming this is minimal. Of course, I could throw in more particles, it wouldn't be true anymore, but let's take the minimal case. And in minimal or roughly minimal, well, in pretty much any gauge mediation, M3 is much less than a TeV. So the gravitino is light. And so, in this case, the LSMSP is not the LSP. So what? Gravity? I'm including here by what I mean by this is SU3 cross SU2 cross U1. Let's not bother with semantics here. We have more important things to do. Now, the physics importance is the point. This is a very different case from this. In this case, the LSMSP has to be neutral and colorless. And in this case, it doesn't. And not only that, it will decay. So the phenomenology is completely different, potentially. So that's what I want to now go through. Okay, now what do typical supersymmetric models look like? Well, there's a huge variety of parameters, as we saw. So what I'm about to say has about 80 pages of fine print, but we only have a few minutes, so you're only going to see the large print. A typical supersymmetric model, that is to say there's wide classes of them that have this property, sometimes for different reasons, will end up with most of the colored particles, the gluinos, the squarks, relatively heavy, maybe up towards the TeV scale, and those particles which carry electroweak quantum numbers, relatively light. So the sleptons and the neutralinos and charginos. The neutralinos and charginos being mixtures of what? The charginos are mixtures of the winos and the charged Higgsino. The neutralinos being mixtures of the neutral wino, the neutral Higgsino, and the thing which is the superpartner of the hypercharged boson, often called the BNO. Because people use B for hypercharge instead of X. Okay, history. Okay. These particles are all mixed up with each other. Right? There's some very complicated mass matrix, and you have to diagonalize the mass matrix and find the eigenvalues. Just as with the Higgs theory, you may have to diagonalize things. Right? Well, with the Higgs sector, you may have to diagonalize things. You have to diagonalize these. That's not the only thing you have to diagonalize. It's often the case, if there are sufficiently large A terms or tan beta, whatever, that in the bottom and top squarks and the staus, the third generation, often the partners of the left-handed stop and the right-handed, the partners of the left-handed top and the right-handed top can mix and do. So you end up with states that are split a little bit. So, for example, one of the staus could be up here and the other stau could be down there. It's a complicated story. I won't go through it. But it's just something to keep in mind, that the spectrum of particles that we see is not in a clean one-to-one match with the parameters that are going into the Lagrangian. So not only are we going to have to find all these particles, we're going to have to find all the mixing angles and then invert the matrices before the prediction that comes out of some higher theory is really fixed. Now, yeah?
So are there any explanation that the partner of light quark is always heavier than
No, I could move that around to some degree. It's typical that it comes out this way in many people's models, but I can't give its proper discussion. The really important thing, though, is that there's lots of different ways the colored stuff could be heavy. So, for example, in what Michael discussed this morning, the masses of colored things have an alpha S in them, and the masses of less colored things don't have an alpha S in them. So simple. On the other hand, if you have a model which is defined up at some very high scale with grand unification, all the masses start out around the same size, but then as you run from high scales down to low scales, the effect of the running is larger for those things that carry color because the beta function for these masses is bigger, and they all get pulled up. It's relatively easy to move these masses around over here, however. So a constraint in a supergravity model would be that either the LSP is the lightest neutralino or the sneutrino. Those are your only two options. And because the sneutrinos are kind of mixed up with these guys, that doesn't happen too often in models. So most gravity-mediated models that are minimal, don't have anything extra, this is your LSP. Now, what does the physics look like? Well, this is we're dealing with the LHC, so we're dealing with color in the initial state, and so it's easy to make colored things and harder to make colorless things. Now you'd say, well, but these things are lighter. However, it doesn't compensate. Most of the time, the heavy colored things are still produced more often than these. And even if they're about the same, the decays of these things are more spectacular and often easier to pick out. So let's just talk about the production of something colored. For example, we might have quark glue goes to gluino squark. I won't be too specific because I'm going to give you the rough idea of how this works. And typically, the gluino will have to decay to Q bar and some neutralino, or chargino, which then in turn might decay, let's say, to a lepton and a slepton, which then might decay to another lepton, and the LSP. Meanwhile, the squark has to decay to a quark and some, let's say, chargino, and maybe that decays to two more quarks and the LSP. Now, what's going on here? R parity. R parity is dominating everything. Again, not supersymmetry. R parity. Since R parity is there, the superpartners have to be produced in pairs because we're starting with an R parity even state. We have to end with an R parity even state. Now that we have something that's R parity odd, all the way along this line, there has to be an R parity odd state. So this has to decay to something R parity odd plus standard model stuff, another R parity odd thing, another R parity odd thing. And the last one is stable. So this is classic supersymmetric signature. There are some jets that are high PT. Spectacular. There are some leptons, maybe if you're lucky, or jets, which are relatively moderate to low PT. Leptons would be great. These are not so useful. And then, because of these two particles, you have substantial invisible stuff rushing out of the detector, so you have a large missing energy signal. So jets, leptons, missing energy. That's typical supersymmetry. Of course, it's also typical of lots of other things. There are lots of other models that have patterns like this. Colored stuff heavy, less colored stuff less heavy, something stable to be a dark matter candidate, or they just have some new global symmetry, so there's some stable particle in there. So this is characteristic of supersymmetry, but not definitive. Nonetheless, that determines what we're looking for, and Jason will describe a little bit of that today. OK. Any questions? Probably you've all seen that before. All right, now, on the other hand, if we go to gauge mediation, it's quite different because, for example, well, first of all, just on general grounds, in this case, because the standard model superpartner, which of the standard model superpartners I've drawn here, will decay eventually to the gravitino in gauge-mediated models. So I've drawn it here. You would have the same process here, where the LSP in the end decays to something. And if it's a neutralino, it could go to a photon, or a Z, or a Higgs. Those are the three possibilities. And in some models, it's mostly photons. In other models, it's mostly Z and Higgs. Okay. So now, instead of our big, everything else is the same, but instead of our missing energy signal, we have now less missing energy and possibly 2 photons. Well, that would be great. 2 photons and missing energy in every single SUSY event. Photons are easy to measure, as we learned. It's like SUSY events are coming along with a little flag that says, hi, I'm probably SUSY. It's much, much easier than anything. I mean, it would be great if this were the case. If, on the other hand, they're mostly going to Z's, it's not so simple because Well, Z's are great when they go to leptons, but they only do that a few % of the time. Mostly they go to jets or missing energy. So it just makes the event more cluttered, a little harder to measure. And you have less missing ET, which makes it less distinctive. Standard model processes also produce missing ET, and the more missing ET you've got, the more unusual it is. So you can make things, again, easier or harder depending on exactly what the structure is here. But the important thing is that, well, it's different, and it's not the only option. Any questions about this so far? All right. Another possibility in gauge mediation is that you move these things around a little bit, and the lightest guy is the STAU. So then you have to first have all the superpartners in the standard model decay down to the STAU, and then you have to have the STAU decay to the gravitino, plus a tau. So how does that work? Well, now we have maybe the same process, same neutralino, but now it decays to tau plus STAU. And the STAU eventually decays to tau plus gravitino. So what do we get in our events now? Every event comes with 4 taus, plus a little bit of missing energy. Okay, totally different signature, dependent critically on who's heavier than who. Again, as theorists, we've barely changed the model. We've taken 2 parameters, one which sets one which sets the fermion masses, one which sets the gaugino masses. We've adjusted them very slightly. We take the minimal model that Michael wrote down, and we make it a little bit non-minimal, so these things move around a little bit, and the phenomenology changes 100%. Instead of 2 photons, it's 4 taus. Okay. Now, one very interesting thing in gauge mediation is that the lifetimes of the LSMSP, which is usually called the NLSP in this case, for next to lightest superpartner, but even that may not be true. Okay. The NLSP has a lifetime which can be quite long. So not only can we have these decays, but they can occur late, halfway through the detector. So this is something that this relates to what Jason talked about in his second lecture, where he talked about the possibility that you have your nice SUSY event with all the jets and a lepton and more jets, and then you have 2 of these particles, which are, let's say, neutralinos, and they decay suddenly to a photon plus a gravitino. So you have photons coming out at funny angles. And if you can detect the fact that the shower that the photon makes doesn't point back to the origin, you actually have a way of detecting it. Or maybe it just arrives late, and so by time of flight, you can see, well, it's not consistent with something having come from the origin out to here. It had to have taken a funny path. So people have thought a lot about how to look for that. Another possibility is that the STAU is long-lived, and if the STAU is long-lived, then instead of this picture, you'll see, in addition to whatever standard stuff is coming out, you'll see particles which look like muons, but they're a little slower than they should be given how high PT they are. You can measure the PT from the curvature of the track. If it was a muon, it would be really fast, but this thing may not be so fast. In that case, it'll be high, or anomalously ionizing, highly ionizing if it's slow enough. It will arrive late, and you can use those various facts that you've measured the velocity, essentially, and you know the PT to measure the mass. And there'll be 2 of these in every event. Again, couldn't be easier. Every single SUSY event comes with 2 of these muon-like objects. My God, that would be great if we see if we get that. All right? It's also possible to have stops or gluinos be the LSP and the NLSP in some models. In that case, you can get other funny behaviors because a metastable stop quark will make a weird hadron, which will behave strangely in the detector. We don't completely understand it even. But people have looked for such things, and we know a lot about it. So what you learn from all of this, if you haven't learned it already, is that the map from models to signatures, which are what experimentalists actually deal with, is an extremely nonlinear map. It's as bad as genotype and phenotype in biology. Okay? You cannot predict by just looking at a model And if you change it a little bit, you'll have anything like the signatures you thought you had before. And so if anyone tells you this particular thing is a signature of supersymmetry and it's a smoking gun, okay, it's never true, especially if you go beyond the minimal model, but even usually if you just change parameters within the minimal model, because it's typically pretty easy to go to a different regime where the signatures are very different. And the converse is also true. Just because a signature is characteristic of supersymmetry doesn't mean it won't show up in other models. So when we see what we see at the LHC, we have a lot of work to do. We have to, we'll make guesses, of course, about what it is we're seeing. There'll be multiple guesses. They won't be mutually exclusive in terms of the signatures that we know so far. They'll predict different signatures for what hasn't yet been looked at, or for what there hasn't been enough data. Gradually, we'll get more and more information about what is actually in the data. We'll have to measure masses, or at least mass differences, as best we can. But as Jason will describe, that's not trivial. These things don't come out with a little number on them. You have to actually do a hard measurement to figure out what the masses are. They don't, branching fractions and cross sections are not that easy to measure in many cases. Testing whether, I mean, supposing I told you magically that I had all these particles, do you know it's supersymmetry? You'd probably guess it was, but of course supersymmetry makes predictions for coupling constants. Not so easy to calculate those. I mean, not so easy to measure those, right? So we've got it's been a long, long period between the measurements we make and being sure that we have supersymmetry. And it could very well be that what we actually observe looks nothing like the supersymmetry we expect, and it'll be 5 years before people realize, it is supersymmetry, it's just not the one we expected. It's got some weird properties, weird decays, some extra particles that make the cascade decays different from what we expected. So don't give up if it doesn't look like supersymmetry, and don't be sure if it does look like supersymmetry. We've got a lot of work to do. Yeah?
So this is just something I've always wondered about this. So if you really wanted to say it was supersymmetry, you'd have to somehow be able to get at the spins of the particles?
Yeah, the spins of the particles can, to some degree, with some difficulty, in some circumstances, be measured. And the reason is that there are matrix, these decays actually have some non-trivial angular structure in the matrix elements. So it can be done, but it's not easy. You need a lot of data.
Yeah. But do you think that they will have it after, I don't know,
Jason's here.
some number of inverse femtobarns?
Look, I mean, the problem with trying to say anything about numbers of inverse femtobarns is I don't know where these masses are. If I move them from 0.5 to 2 TeV, I change the production rate by a huge amount. What you really might want to ask is what kind of statistics do you need? How many events would you need to make a measurement like that? Surely hundreds of any given process. Yeah. Mainly because, it's relatively easy to see you have an excess. But to get a shape of something, you need an excess in multiple bins. And if you're trying to tell the difference between a scalar, which has a shape like this, and a fermion, which has a shape like that, well, you really need good statistics in many bins. And that just sort of sets, well, if you have 10 bins and you need 20 events per bin, okay, minimum.
Because I've heard people say that because of this, no matter what the supersymmetric model is, it will be 10 years before we pin it down.
I would say it will be 30 years before we pin it down, because there will be things about the LHC, there will be things about the supersymmetric model which cannot be measured efficiently. I mean, look at all the parameters. Michael told you there's 100 parameters. And there's degeneracies between them. I mean, how long is it going to take to figure out the mixing angles among all of these guys?
Isn't this a good argument for an ILC where you can do something like spin?
It's a very good argument for an ILC as long as we know what energy to aim at. If it turns out these particles are so heavy that a typical ILC with current technology would be unable to reach them, then it would not be a good argument yet. But there are very good arguments for an ILC after we have some idea of what we're looking for. It's hard to make the argument, and the reason that argument has not succeeded is partly cost and partly because we don't know whether an 800 GeV ILC will be enough. So we better see something first and then figure out what the mass scale is and then talk about the ILC. But yes, there will be very good arguments for it, and perhaps for other machines if we're clever. Okay. Good. Any other questions? All right. Obviously, one could give multiple lectures on supersymmetry, but there's also good reviews. So I don't think I'm leaving you. This basic picture of what the options are and what the likelihoods are, I think, is enough to carry with you for daily use. Composite models, now I'm going to say some words about. And I'm going to say less, in a way, at least less detail, although I will try to characterize for you I will try to make links between the motivation behind or the mechanism behind a particular model and what it tends to predict. But the thing I want to re-emphasize is that the problem that all of the compositeness models have, and the reason why it's very hard to believe any particular one, that isn't to say I really am confident that Higgs isn't composite, but they all have to deal with this problem of the Yukawa couplings. And they all run into trouble there. All of them. There are no really satisfying models of composite Higgs. This despite the fact that a composite Higgs model, at least the mechanisms behind it, are really very beautiful, and it would be very nice if it were true, because in fact we know of mechanisms that could give a very nice composite Higgs and break electroweak symmetry in precisely the way that it's supposed to. And we've already learned about them. I've already written down this potential twice in this course, and I'm going to write it down again. Or I won't actually write it down again. I'm going to remind you of it. I wrote down the Higgs potential, and I wrote down the potential for the pions. Okay, let me remind you about QCD. So in QCD, we have, in QCD with two flavors, let me ignore the strange quark for a moment. I'll come back to it. So what I'm going to describe now is the mechanism behind Technicolor. Okay. Now, Technicolor is, as I just mentioned, a beautiful idea. None of the models really work, but it's such a beautiful idea. Maybe it's true, and we just haven't been clever enough, or there are things about quantum field theory dynamics that we don't know. But it's tricky to make it work because of the flavor. Now, we know that in QCD, we have SU2 cross SU2 breaking to SU2, or more precisely, QCD with two flavors. Just as very similar to what we have in the Higgs mechanism, where we have SU2 cross U1 goes to U1. And in QCD, this occurs at around the 300 MeV scale. So why couldn't we have a variant of QCD? Just take QCD as we know it, make another copy of it, and these SU2s will identify with the SU2, well, a U1 inside of it will identify with the SU2 cross U1 of weak and hypercharge. Why not? Perfectly reasonable idea. And the only thing we'll change is so we'll gauge the SU2 and U1 subgroup, which sits inside the other SU2, and we'll do this at 246 GeV instead of at 300 MeV. And then we just look to QCD to see what QCD does, and we'll know what Technicolor does. So what does QCD do? Well, it has some pions. In massless QED, these would be massless. So let's take massless QED with two flavors. So we have Nambu-Goldstone bosons, which are massless, pi plus minus and 0. Further up, we have a rho meson and an omega. And we have this very broad thing, the sigma. And rho mesons are unstable. They're positive, negative, and 0 in their charge. It's a triplet. They all decay to pi pi. The omega decays to pi pi pi. The sigma decays very rapidly to pi pi. Okay, those are the basic things about QCD we need to know. What happens in a Technicolor-like model? Well, instead of the pions, what will we have? I called them G's. We would have the G plus minus and 0, the now would-be Nambu-Goldstone bosons, which will get eaten. And so, I'm sorry? Yes, this is not, I understand what you're saying. I was trying to draw a subgroup of. Let me do that better. This is a U1, which is a subgroup of an SU2. And then this thing breaks to U1. Thank you. So there will be, if you turned off the gauge couplings, there would be an SU2 cross SU2 global symmetry. With the gauge couplings on, you have SU2 cross U1 gauged, and that breaks any remnant of the remaining SU2 explicitly. And then you have spontaneous breaking. Well, since you've gauged it, it's not really spontaneous breaking. You have the Higgs mechanism giving us a massless photon, and the W plus minus and Z, which are no longer massless, of course. Okay, and then we have, let's call it a techni omega and a techni rho, and we even have a techni sigma. What's the techni sigma? Right, that's the Higgs. And it's very heavy and very wide and decays very rapidly to what? Goldstone modes. Remember this? Okay, if you take the Higgs and you make it self-coupling very, very large, what does it do? It decays very rapidly to Goldstone modes. It becomes very, very wide. That's just what's happening here. The sigma naught it's part of a composite in this model. It has a strong self-coupling. It couples very strongly to pions. So it decays very rapidly to W and Z pairs. End of story. The rho Technicolor, on the other hand, is something interesting because it's a relatively narrow resonance, and it can couple to W and Z pairs. How are we going to make it? How are we going to produce it at the LHC? Couples to W and Z pairs. How do we make the Higgs at the LHC? There are three ways. One of them involves W's and Z's. What's that called? There was gluon fusion. There was associated production, W Higgs, and then the other one's called weak boson fusion. So somehow we're going to make W's. Let's say W plus, W minus. For example, the initial state could be a D that turns into a U, and a U that turns into a D. Notice these involve the valence quarks only, which is good. This is not a QQ bar initial state, and that's great because we don't have a lot of QQ bar at the LHC, but we have plenty of valence quarks. And then we could produce the Higgs if this is in the spin singlet channel, or we could produce the rho Technicolor. Either way, we're affecting the scattering of longitudinal gauge bosons. All right? Whether you put a Higgs here or you put a rho. The point is that because the longitudinal gauge bosons are secretly these Goldstone modes, and the Goldstone modes are strongly coupled through the strong dynamics to each other and to everything else, what we expect to see in a model like this, with the scale relatively low, remember the rho meson is at 770 GeV, so you would expect these things naively at a TeV, is that we'll see strong scattering of W's. Only the longitudinal W's. Transverse W's will do what they did before, but the longitudinal, well, to a large extent, but the longitudinal W's will start to really show signs of new things. Now, the problem is twofold. One is that electroweak precision measurements tell us that the Technicolor scale can't be that low. These particles have to go up. 3 TeV, maybe? Well, that's a big cost. You go from 1 TeV to 3 TeV, your Parton distribution functions drop a lot. It's hard to get these W's. And also there's a background, because, of course, in the standard model, you can have processes that look like that, just with standard model interactions here, W or Z exchange or just the 4-point interaction, for transverse W's. And they're big enough to pose a significant background to that. One of the reasons why the SSC would have been a better machine is that the ratio of this to that would have been bigger. So if we're in this situation, we ought to hope that there's at least one other signal to look for, because this is really hard, and it will be a decade. We're going to have to go to very, very high luminosity to see this, if that's the only thing we have to look for. Typically, of course, models are a little richer, and there are other things to look for. But that's part of what makes Technicolor in its original form a little bit difficult for the LHC. Or in general, any very, very heavy Higgs with a large self-coupling gets tough. Fortunately, electroweak precision suggests this is not the case, right? So, but good to know. Any questions? Now, in most variants of Technicolor, again, you have to deal with a flavor problem. So you have to deal with the fact that the top quark coupling somehow got to be big. And so at the very least, the top quark often participates in this dynamics. And because of that, often, when you actually write down explicit models that solve that, the top becomes interesting. So not only do you have, in addition to W and Z bosons, rho mesons with the same quantum numbers, just much heavier. And of course, if you really keep tracking QCD, there's a rho, and there's a rho prime, and there's a rho double prime, rho triple prime. Here there's a rho, and there's a rho prime, and there's a rho. I mean, there's actually tower states with the same quantum numbers of the W and the Z in such a model. If you add the possibility that the top is composite, then not only will you have the top here, but typically you'll have a T prime somewhere, and maybe a T double prime. You'll have excited versions of the top, or something else up there that carries top quantum numbers. The top is relatively easy to produce. Top primes are also relatively easy to produce because they're colored. And a typical situation is a top prime might decay to a top plus a Z, or a W plus a B. So these things, in models that actually deal with flavor in a successful way, are often present and very interesting to look for. So the lesson is, in models like this, we expect W partners, Z partners, and top partners, strongly coupled, and hard to produce in this case, but maybe not so hard in that case. Okay. Any questions? So this comes back to my original statement 2 lectures ago where I talked about the third generation. One of the reasons we're so interested in the third generation, being able to identify it, is because we might be looking for things like this. Or in a supersymmetric model, we want to know about stops and taus because they're special, they're different, they have mixings, they move around. We want to find them and identify them and study them carefully. That requires identifying B's and tops efficiently. Okay, let me mention one other qualitatively different idea. Any more questions about Technicolor-like models? The basic idea of Technicolor was that the Higgs is the sigma. Here's a different idea. And the precise version of this, any reasonable version of this idea does not use this analogy precisely. So I'm not going to write down any particular model. I'm just going to kind of motivate a general idea. The idea is that let's now consider not 2-flavor QCD, but 3-flavor QCD. And notice that if we do that, so this is now we have an SU3 cross SU3 broken to SU3. We have pions, we have an eta, and then we have kaons. Right, this is our octet. This is a traceless matrix. It's our octet of Goldstone, of Nambu-Goldstone bosons. Now, supposing I put SU2 in here, and U1, well, actually, sorry, I'm going to put SU2 cross U1 inside this diagonal SU3. You'll notice this has the quantum numbers of the Higgs. It's a doublet with a little bit of hypercharge. So here's an idea. Maybe the reason the Higgs is light is because it's almost a Nambu-Goldstone boson itself. This is an old idea, but it doesn't quite work initially, and it's only been relatively recently that it's been made to work a little better. Now, of course, what do we need? If this is light because it's a pseudo-Nambu-Goldstone boson, we still need to make sure it develops a potential, like the ones we've always been writing, so that it then condenses and has Goldstone modes, which are, pieces of this doublet, and a Higgs, which is the fluctuations of the expectation value it develops. Okay, so there's 2 steps here. First, we have some strong dynamics which generates these Goldstone bosons, which are not quite Goldstone bosons because there's some breaking of the symmetry. Because there's a breaking of the symmetry, unlike a Nambu-Goldstone boson, the kaons have a potential. Right? Nambu-Goldstone bosons have a flat potential. These guys will not have a flat potential because of the P here. And if the potential is the right shape, then they can develop a VEV, break electroweak symmetry, and the strong dynamics will, in general, be higher in energy compared to Technicolor. Because in Technicolor, the dynamics of the strong dynamics and the Higgs mass are at the same scale. Here, we're going to have strong dynamics at the 10 TeV scale, and we're going to have a Higgs which is down here. It's suppressed by the fact that it's a pseudo-Nambu-Goldstone boson. It's not the sigma. It's actually like a kaon. Now, making models like this actually work is not entirely trivial. That's why it didn't work the first time in the late 70s, early 80s. And the tricks that are involved involve an idea called collective symmetry breaking. And at least there's more than one trick, but one of them is called collective symmetry breaking. The idea there, I'm just going to say it in words, but listen carefully. The idea is that you have, the word collective means that you have actually 2 symmetries that are being broken. And if you break, so let me say it again. You have 2 symmetries which are being spontaneously broken, but they're each a little bit explicitly broken. If both of the symmetries are explicitly broken, then this particle is a pseudo-Nambu-Goldstone boson. But if either one of them is not explicitly broken, again, they're both spontaneously broken, but if either one of them is not explicitly broken, then this becomes a true Goldstone boson. Now, what's the point of that? When I break a symmetry, and I turn a Nambu-Goldstone boson into a pseudo-Nambu-Goldstone boson, it picks up a mass. Where does it pick up a mass from? Some loop graph. For example, if I have a symmetry, which is exact when a gauge coupling is 0, and then I turn on a gauge coupling, what's going to happen? I'll have some Nambu-Goldstone boson, and it'll pick up a mass through some interaction. In fact, that's what happens in massless QCD. If I take massless QCD with two flavors, I have massless pions. Turn on electromagnetism. What happens? The pi plus and pi minus pick up a mass because of this graph. Right? They discover, oh, wait a second, we're charged. The symmetry that we transformed under is partially broken by that. So there's some loop graph, and it involves some couplings. Well, the trick here is that they're going to be more than one graph, because there's two symmetries. And no, I didn't say it right. Let me say it better. Actually, I'm not sure I want to go down this route because I'm just looking at the time. I'll tell you what. Let me say it this way. The way these models work, have to work, is that there's going to be some additional cancellation necessary to suppress the Higgs down with a large enough mass. And now let me tell you how that works. Maybe this is the best way to go. Let me tell you how this works. So the natural scale for the Higgs mass is the strong coupling scale. That was the usual argument about the hierarchy. So if I'm telling you that there's some way to keep the mass low, how's it going to work? There has to be some explicit way of seeing it. Here's how it works. So one thing for sure is that one thing that breaks the symmetries that would protect the Nambu-Goldstone boson is the gauging of SU2 itself. One thing which can appear here is the W boson. In other words, as we know, the Higgs boson mass gets a correction from a W loop, which is potentially quadratically sensitive to the ultraviolet. Okay, there are also diagrams. If this thing couples to the top, and it better, right? So our Nambu-Goldstone boson is going to get corrections from the top. These are just the usual Higgs corrections, the Higgs mass corrections that are bad. And I'm telling you that no, those things do not push me up to 10 TeV. How is that possible? There must be some canceling graph. So what I'm telling you now is that collective symmetry breaking is clever. It pushes the mass down, and it does it in the following way. It makes sure that there's a W prime in the game. And it arranges that the coupling constants, the product of these coupling constants, is minus the product of those coupling constants. In other words, at one loop, these two graphs almost cancel. But unlike supersymmetry, where there's a similar cancellation at one loop, these particles have the same statistics, just different couplings. Same with the top. There'll be a T prime, but the coupling will be such that there's a minus sign. Now, so let me compare and contrast this with supersymmetry. In supersymmetry, particles have superpartners with opposite statistics. Therefore, the loop graphs come with opposite sign. That's why you have a cancellation. Magically, this happens to all loop order. Here, we have something interesting, different, weaker. We have particles and partner particles with the same statistics, same quantum numbers, but couplings which, because of the symmetry structure, end up automatically arranged so that they're in relative minus signs. Only at one loop. So whereas in supersymmetry, we can take the cutoff and push it all the way up to the Planck scale, in a model like this, we get one loop factor, roughly speaking. So instead of having the strong coupling scale at 1 TeV, we can have it at 10 TeV. But a prediction of this model is that there will be partner particles for the W, the Z, the top, the Higgs, all the things that make the Higgs mass change a lot in the standard model must have partners so that these loop graphs can cancel. So we have a prediction. Look for W primes, look for Z primes, look for T primes. And that's not so different from what I had over here, where I had rhos and maybe T primes, except the rho is a very strongly coupled particle. These particles will be perturbative and weakly coupled. The strong coupling won't kick in until 10 TeV, out of reach of the LHC, but these particles, these partners, will not be out of reach. Okay, so those are two distinct compositeness ideas. The Higgs is like a sigma, or the Higgs is like a kaon. All of these models have potential flavor problems that one has to deal with. Not surprising, the flavor problems might be a little less bad because you can push some things up to higher scales. But still, it's not so easy to make it work. There isn't some sort of preferred beautiful model. There isn't any beautiful model. And one of the problems is just getting the top quark Yukawa coupling to come out right tends to be a little complicated. This is the basic principle. It's very pretty. Just listen to Technicolor. The basic principle is very pretty. The reality is not so pretty. But it could be a lack of ingenuity on our part. Yeah?
some seems that.
Yeah, it's not obvious how this works, but I didn't myself think of a quick way to explain where the signs come from. The experts, there are nice articles on little Higgs that actually do explain this, and they will do a better job of explaining it than I will trying to remind myself the reason in 2 minutes.
So we don't have much enough to
No, it's not that. No, it's that you have mixing angles is what you have. Right. Signs of mixing angles can be negative. Okay. Good. Now, just a remark. Obviously, again, for both of these classes of models and for others, you can take this idea, abstract from it the basic idea, and do the same thing in an ADS model. And then you're doing Randall syndrome style model building, where you take a 5-dimensional or even 10-dimensional, but typically 5-dimensional model, where you just sort of say, well, there's some ADS version of all these things, right? And you just take the dictionary between ADS and CFT. All the global currents turn into gauge bosons in the bulk. And weak gaugings are easy to understand because you weakly gauge currents both from the field theory point of view and from the gauge theory point of view. And Goldstone bosons you can understand, and breaking of symmetries you can understand. All this stuff can be done in the ADS language. The hope, of course, is that the models I've described here, if you do them in the field theory language, they're perturbative at high energy, they're QCD-like, therefore they're small tuff coupling models. And the hope, of course, is if you do it in the ADS language, where you're really dealing with a larger tuff coupling model, that they might be qualitatively different, and maybe some of the problems that you have would get solved. I think it's fair to say that was attempted. You don't really get much. You get some things in some cases. It's not really as though, what it would have been nice is you could show that a Technicolor model built in 5 dimensions had a much smaller or maybe even different correction to the electroweak precision measurements, and therefore, instead of being a problem, would actually be good. Well, that doesn't really happen. Depends a little bit who you talk to, but I don't want to downplay the fact that these ideas are really very beautiful, and one of them might still be right. And so what we're looking for in these cases is always partner particles. Just as in supersymmetry, we're looking for partner particles. But the particles for which we're confident there will be partners are the ones which are involved in the strong interactions in some way, namely the ones that couple strongly to the Higgs. Since to cancel off the Higgs mass sensitivity, you've got to have these cancellations, which in this case come through perturbative loops, and in this case come through strong dynamics, but in both cases involve partner particles of some sort. Okay? Injury time. Okay. So I've told you at the beginning of the class that there are 2 other things you might think about. One of them is that quantum field theory is going to break down. Why not? Well, why not? Because we should have seen signs of it already. But if you can hide it sufficiently, we know of ways that quantum field theory will break down. We know of things in string theory that are weird, like non-commutative field theory and little string theory, strange types of compactifications that are hard to interpret. Maybe what we're looking at is something which is going to be hard to interpret in terms of quantum field theory. And maybe really won't work in terms of quantum field theory, and yet is not as dramatic as saying the Planck scale's at 1 TeV, which might really be hard to understand. Because if the Planck scale's at 1 TeV, flavor also has to be at 1 TeV. But maybe there are ways for quantum field theory to break down where you don't screw up flavor. That would be interesting. We don't know of any. The other possibility that we're looking at is that it's one of these models that I've just described here, but on top of everything else, it's not minimal. And then all hell can break loose as far as the experiments. There's tons and tons of models which would pass Occam's razor, which would not pass Occam's razor, which pass Strassler's machete in here. Okay? You can have many more weird signals than I have described. I've listed a few. And the important thing is not that I think any particular one of them is going to show up. The important thing is that any one of them could show up, and we had better be sure we're prepared. So I personally have spent a lot of time, and I haven't given any lectures on this, but my collaborator, Catherine Zurich, gave some recently here, on classes of models called hidden valleys. There are other models which are out there, but hidden valleys are particularly interesting because, for example, in a hidden valley, you can take something like this in a gravity mediation model. Remember the gravity mediation model? Gravity mediation was simple. I just erased all of this stuff. Okay, you just had missing energy. Okay, that's how you know it's gravity mediation, because you have missing energy. Unless, of course, in addition to these particles that are in the standard model sector, there's another sector. And maybe it has particles which are, have a spectrum like this. So then this is the LSP. Oh. Well, now we have all the same considerations we had for gauge mediation. Remember, in gauge mediation, the LSMSP wasn't the LSP. Now we see in non-minimal gravity mediation that also doesn't have to be true. And so all the considerations about the neutralino being stable and being the LSP and being a dark matter candidate are out the window. And we can have all those same classes of decays and more. And not only that, whereas in gauge mediation we would have something like, let's say, photon and a gravitino, now it can be photon plus this particle. And then that particle decays, and that particle decays, and some of these are LSPs, and they're invisible. And if that's all it was, it's just missing energy. But in many hidden valley models, what happens is this. Some of these particles decay back to standard model particles. And suddenly the events are much more cluttered. Some of these particles could be long-lived or not. And the number of signals that can come out when you start considering the fact that we have no electroweak constraints on this. You think about how complicated those sectors could be. I mean, look at how complicated our sector is. This doesn't have to be very complicated for the complexity of signatures that arrives as the LHC to be enormously interesting, complex, difficult, and hard to interpret, and very exciting. So keep your eyes wide open. There's all sorts of things that could happen with this experiment, which would not have been seen before, because at the Tevatron, you're not producing this. You don't have this process going on. At the LHC, you turn on, and suddenly all these light particles, which you didn't know were there, because they don't carry any standard model quantum numbers, suddenly start showing up. So finally, let me just say, this machine is really important, in case you didn't recognize that. Right? We've been bottlenecked in terms of what our understanding of nature is for 30 years. And this machine has the best chance to break that bottleneck. And it had better work. Okay, I don't really think I need to say much to you about what will happen to our field if it doesn't work. Or if it does work, but we don't drag much out of it. So it's really important as theorists to do our part for our own self-preservation, if nothing else, to make sure that this machine gets the most out of its data and doesn't miss anything. Okay, we will not have a competing machine for years, and if this machine isn't remarkably successful, there won't be an ILC, and there won't be anything else for that area of the field. So keep your eyes out for theory bias, keep your eyes out for blind spots, and pay attention to what the experimentalists are doing and help make sure this machine is a success. Thanks.